Or I think if you go to the bottom left corner,
okay,
that's going to be a new tab, like a kind of blurry tab will pop up, and then you can change into pointer, laser pointer.
From where?
From the bottom left.
From Zoom? From Zoom?
Yes, the same. Yeah, the same view that you see, on this slide. Just go to the bottom left. Yeah, somewhere there on your slide.
On my slides,
because we are seeing only your screen. Whatever you choose from. Tell me, are you running from the PDF file to?
I'm the PPT file.
Okay, it's the.
So basically, I just want to have the laser pointer inside. You can see my cursor, right?
Yes, I see that. Yeah.
I thought if I change into laser pointer, I'll probably make it.
But I think you should set it from the software that you are actually using to show your slides. Is it PowerPoint? Then
it's PowerPoint. Okay. It's not from the Zoom.
I think if you right click in the slide, and then there's an option that says pointer.
Screen.
It says pointer options.
Pointer options. Just below the screen.
Okay, pointer options. Thank you. Oh my God.
Yeah.
Laser pointer. Here we are.
There you go.
All right. Well, thank you.
You're welcome. Perfect.
Thank you. We all become experts. You become experts. I'm sure. Thank you.
All right. I think we can go ahead and start. Hi, everyone. I'm pleased to introduce our guest speaker today, Dr. Zhong Lu from SMU. As you probably know, Zhong finished his education in geophysics through bachelor through PhD. He did his bachelor and master in University of Peking in Beijing. And then he moved to University of Alaska for doing PhD between 1992 to 1996. And between 1997 and 2013, he worked for different departments as USGS as a research scientist. And then starting 2013, he joined to SMU as a professor. And mostly he is interested to analyzing satellite data, including InSAR and SAR. So his research interest relies on satellite data, as I said, but he's mostly interested to develop new techniques in order to look at the data. And he already developed new techniques that it's quite common, and other scientists actually using these techniques for research and teaching purposes. His research highlights actually covers the subsidence subject on the Gulf of Coast, landslide studies, and InSAR imaging of volcanoes. So please join me to thank Zhong, and please, Zhong, have your time, and we are here to hear what you are going to show us.
Well, thank you, Murtaza, for the very nice introduction. Hello, everybody. It's really good to meet you in Zoom. It's a city that we are about 30 minutes away, and I can definitely wave my hands in front of you, but just because of the situation, let's do it massively through Zoom. So I gave a talk about 3 years ago about how InSAR can be used to study the natural and human geohazards. So thank you for inviting me again. So I think before I talk, I just want to have something less. Before my talk, I want to highlight the importance for measuring the Earth's surface deformation, and particularly measuring deformation in a cost-effective method at any time, anywhere in the world. So let's start. That is, the Earth's surface deformed in response to various of solid Earth processes, including both natural and human processes. for example, volcano, landslide, and earthquakes, and as well as anthropogenic groundwater hydrocarbon interactions and sequestrations. So it's in some cases that the deformation over time can be a diagnostic of the ongoing subsurface processes. It's just like when you use the seismology or some other TPS measurement, you can see what's going on. So therefore, take the deformation measurement, you can see, try the processes, you can try to apply the inverse theory and to understand the causal mechanism. In some cases, like your GPS, like the deformation itself is a very important part of the product already. You can predict it for infrastructure monitoring. In some cases, like the deformation may signal a forthcoming catastrophic events. So it's in this context, the National Academy of Science and Medicine engineers decadal survey for earth sciences has designated that measuring surface deformation related to the hazardous geological process is one of the nation's highest priority. I think it's in this context, I would like to show you our latest work. The latest work haven't been published yet at all, but it's being written out. So I'm talking about the latest rate, fixed trend, and the temporal evolution of deformation of the Gulf Coast. So of course done by InSAR. So it's done by a hard worker from my shop, and primarily by Dr. Fei Chu, and she's postdoc, Dr. Jing Kim, and his staff scientist, and Wei Yu Zhang, his PhD candidate. And for the work over the Gulf Coast, we are in collaboration with Mike Turco from Paris Galveston Substate District. So I didn't do any work, I'm just the spokesperson to record what we have done. So I'm going to, I cannot let you leave without letting me into insulting you or telling you a little bit with the InSAR, right? Whether you like or not, I have to tell you because that is the heart, very close to my soul, close to my heart part of the research. That's why I feel every day's research is so motivating and so interesting because these are still evolving on a daily basis. And then I'm going to show you why I want to do this work. It sounds a little bit awkward, but because I want to introduce here, so therefore I'm going to have a background motivation of the Gulf Coast. And so show you the deformation rate that we have mapped so far, and highlight some representative deformation features, and let it conclude my talk. So here we use the InSAR. Before I talk about the InSAR, we have to talk about the synthetic aperture radar. So this is called SAR. What is synthetic aperture radar mean? That the aperture is antenna. So you can say it's synthetic antenna radar. Okay, so we say it's synthetic aperture radar because aperture can be easily applied both optical and radar data. So what do? You transmit the radar pulses and the electromagnetic wave, just to transmit the seismic wave. The chirp wave in this case is also used for the electromagnetic wave. And you can by transmit wave repeatedly and with the sensor moving along along a platform, so a target is being imaged many times. So we use a very similar technology that we use for seismic imaging. We compress data on range direction. We sense that data in the azimuth direction using range migration, whatever technique you use in the seismology, also equally applicable to the synthetic operator imaging. So simply put, when you get a radar signal data, through this kind of processing, you can generate synthetic operator images. So why we have the synthetic aperture radar, why we don't use the real aperture, because remote sensing resolution is proportional to the size of antenna, the aperture. Large aperture, you can achieve very, very high resolution. Small aperture will get you very close resolution. When you put a sensor on space, the resolution for the wavelengths of radar can be on the order of kilometer for real aperture radar. Therefore, we have to use image processing technique. Okay, I think I talked about too much. So we got, when you, after this synthetic arterial processing, you got a SAR image that's basically represent the reflectivity of every ground target with certain resolution, few meters, 10 meters, 2 meters. We now can get 25 centimeter resolution data, like what you see here. So the image has, in InSAR, has two layers of information. One is the amplitude, because the electromagnetic has amplitude that related to the strength of the signal scattered back to the antenna, which can be used to infer the Turing slope, surface roughness, and the physical property of target. In this case, it's pretty much dialogue constant, which is on the Earth surface dialogue constant, pretty much the same, but only changes happen when the moisture comes in fact. So you can see some amplitude that is very sensitive to the soil moisture on the surface of the Earth. The important part is this signal, receive the signal phase. The phase is related to the distance from the side of the ground. So each phase, we recorded a fraction of the wavelengths that executed between the target and between satellite target. So it's in this way that when you combine the data, the SAR data, to SAR data, you can generate interferogram. So this is you take two SAR data, combine SAR data, you apply all the image processing technology you can use and to generate. Here you say the one data path, you can here have another data path from here, you generate the interferogram. So it's the interference of the two SAR signal, basically the phase signal that is used for InSAR processing, and of course, because the electromagnetic wave is wave. The interference is one of the wave phenomena. Of course, 200 some years ago, before Thomas Young, people were debating whether it's particle or wave. But here is a perfect way we can use interference technology and the phenomena to combine the phase information from two images and generate interferogram. So when you have the interferogram, what you can do with it? So you can do one of the two things. One is you can use the interferogram to derive a topography map. So that's called digital elevation model. This is one of the primary technology to generate the DEM on global scale. You say, well, we can use photogrammetry. Yes, you can use photogrammetry, but if you want to do the DEM on photogrammetry on global scale, that takes quite many years. But you can do it with radar data in a couple of weeks on global scale. Well, I cannot emphasize how important, significant digital elevation model everybody need it. Without it, you cannot do earth science, period. I'm sorry to say that, so for modern earth science, right? The second part is, what happens if you already have DEM of this area? Well, you can take that DEM effect out of your interferogram, and then you can generate the surface deformation map. So this is how we generate the deformation map based on two SAR images. And what kind of characteristic you can do? You can get with a ground resolution of 10 centimeters, depending on pixel size of the image. And you can have accuracy about precision about centimeters or millimeters, depending on the condition of target and atmosphere. And with area from 10 kilometers to 300, 400 kilometers of area. So, of course, when you get the deformation images, you can use it for geophysical model, right? So surface deformation, you can apply, use the geodynamic model, geophysical model to understand causal mechanisms. So if you take the two SAR images, you can generate a series products, right? So you can look at SAR, as I mentioned, amplitude intensity data is related to roughness, Turing slope, and dialogue constants. You can see in this case, there's a volcano over illusion, and so before the eruption and after the eruption, you can see the made of the cone, made of the caldera here, this new lava flow. So you can see it from SAR intensity data. So the second part, the second set of product is called SAR coherence. And the coherence correlation is of the two images or multiple images. And the high coherence, meaning that is yellow area here, that is the ground target, were not modified during the time when the two images were acquired. And so near the coast, because of erosion, vegetation changes, snow and other stuff, and then of course the correlation is lower. Here is due to slow, and here due to new emplacement outflow. All these places you can see very poor low coherence. But second part is coherence also can be used to quantify the InSAR precision of the measurements. Of course, we do you can take the 2 images, like 2 optical images or 2 photos. You can track the large surface movement, we call it field tracking, offset tracking, purely based on image correlation technology. Of course, the most important part is the definition image. So here you produce based on 2 images, more images, you generate definition. Here is also definition associated with eruption of the volcano, and you apply geophysical models and to understand the causal mechanism. Here you see where the location of the magma reservoir, how much magma pressure changes or volume changes associated with this amount of definition observed where the location of the magma have to be. So of course, InSAR can be used in the DM, multiple images, multiple DM. The DM difference will allow you to see the thickness of lava flow or some other topography changes. And finally, I won't touch this topic right now. The radar data is polarimetric data. The electrical vectors is the directions we call polarization, which different target of ground surface can respond differently to different polarized data. So therefore, can be used also in further target characteristics. So what we are doing now, this technology has been there for 30 years, and what we are doing these days that if you look at an inner program, look at the pixel, we don't look at the one image anymore, we look at a stack of many images, look at the stack of the images. So this is a 3-dimensional problem, right? 2-dimensional data stack. Each one maybe have 20,000 pixels by 100,000 lines, and has maybe 30 images. You can see you need a large data volume. So every pixel, we look at every pixel, we try to track how that pixel changes as a function of time. And for that pixel, if you look at the interprogram face, it has many different components, as contain the DM error, DM maybe not accurate enough, and can have the atmosphere error that because the atmosphere changing from time to time, right? So orbit may not precise in other nodes as well, including thermal nodes from the instrument. But your goal is try to measure deformation. Therefore, this is a perfect inverse problem, right? Inverse problem that you have many different acquisitions. You try to characterize each different terms and use image processing technology. Or these days, you can use deep learning as well. Try to remove the one you don't want. If the area you want to, the purpose is to look at the deformation, and you just remove everything out, try to reduce and try to improve deformation measurement. And therefore, you can also get time series measurement from the stack of SAR images as well. So now the second, move to the Gulf Coast. So the here show you the background motivation. I think some of you probably geologists and hydrogeologists, I'm sorry, my understanding for coastal process is very shallow, so I won't dive into too much because you know this much more than I do. So why we started Gulf Coast? Well, the Gulf Coast has a lot of interesting phenomena that is really because by the intensive groundwater pumpings and associated with faulting, salt, as well as a very long history of hydrocarbon production. Well, you have production, you have the byproduct which that's part of wastewater, often being injected into the first deeper part of the surface. So all these have resulted in significant substance and wastewater injection can cause surface uplift, and they all can have consequences and can be serious hazards and affect the environmental resources. So our study area covered by NASA pretty much covered from the northwest, from the western part of southern part of Texas, all the way to the northern part of Florida. So it's about 500,000 square kilometers. So imagine if you want to look at this from GPS data, how many GPS you need. So here we show the show the oil field and show the faulting here, lines here, and show the major metropolitan area, and show you the and say here we are going to, and also salt over here. So here we are, our goal is try to see, well, can we map the deformation over the whole Gulf Coast using this satellite uniformity technology. Keep in mind, this hasn't been done before yet, so this will be for the first time. So before I show you the result, let's still try to talk a couple more consequences and effect people have seen due to the cultural substance, because the substance is known. Exact amount, rate, spatial extent, probably don't know, but it's there, right? The substance called wetland loss over here. You can see the Buffalo Bay over area. You can see this is from here, the wetland, the distributions and to the reduction wetland of cows. The substance make the land more susceptible to floodings, and which evidence in the Hurricane Harvey a few years ago, right? Cause substance uplift, also called building infrastructure damages, and this is in the Gulf Coast. Here, take the example from Houston Gulfstream area, Houston area, show what the substance has been mapped, and by the mapping individual sparse locations and then probably all the contour lines, and try to get a very nice map. But do you trust the contour line at this location if you don't have measurement, right? So here we say for the satellite radar image, we can image every locations, and most locations will target have suitable scattering conditions. So come back to a few locations, you can see the substance reached to about meters, and in some locations about 3 meters. And the water, of course, declined for in some locations for them from 1977, particularly 1997, it's reached to about 30 meters. So of course, this is the way our Harris government substance district was established, try to combat for the substance and reduce the substance. So what we did for this work is we take the data sets. So this is we take all the available data sets you can find over the Gulf Coast. So from the ALOS-1 data, and primarily from ALOS-1 data, we also for the few metropolitan cities over the Houston, we also use other InSAR and yesterday. But primarily using for the whole Gulf Coast, using ALOS-1 data, a little bit ALOS-2 data. This is Alban data. This is the data, Sentinel-1 data from European Space Agencies. So how many data types, is each track here for the ALOS-1, ALOS-2 is about, about 70 kilometers wide. And on the northwest direction, it's about 300, 500 kilometers long. And for the Sentinel-1 data, is about 240, 250 kilometers wide. And so we also want to cover the Gulf Coast, northwest direction, about 300, 500 kilometers. So it's about 500,000 square kilometers total. So we use the SMU's mainframe supercomputers to do all the processing, and it's automatic processing through the SAR processing to the InSAR processing to time series processing is done automatically by our mainframes. And of course, the primary author here is Dr. Fei Chu, is not trust. A lot of them she did iterations over localized area, try to refine the environments, try to tease out, remove some of the artifacts in the user environment to improve the environment. So if you know more about stuff and look at her publication 2015, 2019, all available on our website. So we also mosaic adjacent acquisitions here, and try to get the mosaic deformation of the whole Gulf Coast. And so we quantify our environment with 2 different measures. One, we call it precision. So basically precision, you try to measure how repeatability and how we can based on our own data. So what we own data, the satellite data have overlap. We look at the data over overlap area and see whether the data from 2 different independent tracks measure the same deformation over the same overlap area. Second part of how you have to put your feet on the ground. That means you have to compare with the truth. Here we call the GPS truth data, and compare that one we call accuracy. So we do this both precision using the InSAR data alone, and the compare with GPS data as I call accuracy. So believe it or not, how much the data density you need? I think you need more than half petabyte of data, 0.6 petabyte of data over this area. I assume you do know what's the size of petabyte. So here it shows the part 3, shows the average definition rate of Gulf Coast. And I showed it for the first time we produced definition of the whole Gulf Coast. And you can see this, because the whole Gulf Coast, you can see only see the large feature of deformation, right? Houston Galveston area. Here you see something, there's a minor location here. These are northern nodes, I tell you, and the other signals because of large scale. So what is we are seeing here, we compare, we look at the precision about 8 millimeters per year that we can get, that is called 1 centimeter. The accuracy about 1 centimeter per year based on the GPS measurements. If we look at the deformation features, and if we use, say, well, let's use the threshold about 50 millimeter per year threshold, and use the size of the deformation feature about 1 kilometer, we can say about more than 27 substance points. Of course, Dr. Fei Chu is discovering this kind of increase this number, so I don't trust this number. If you ask her for today, this result she gave me probably a few weeks ago, and if you ask results, she probably says it's already 30, because she's improving the measurements. So there's about more than 40 update cones on this number. Of course, is fluid as well. It's probably more than that one already. But here we put threshold about half kilometer in dimension. So here is another average definition map. This takes enormous time as well, based on the data from 2016 to 2019 to 2020. That time period, because Sentinel-1 is a revolutionary sensor because it's large area regular acquisitions. It's free data for anybody. Right? So early SAR data were not free and only available to investigation through proposal or through some commercial menu. Here, because of free data available from the European Space Agency under this, because of more temporal acquisitions, the data stack is very, very deep now. So the precision reached to about 5 millimeter per year. The accuracy also reached 5 millimeter per year. So more deformation feature can be identified over different locations. And of course, the transient detail can be revealed by this environment as well. So as I mentioned, that we compare the GPS data with available, compare InSAR measurement with available GPS data. Here we show GPS locations and give you a few examples. For example, over here is GPS measurement in gray and the red and blue dot from the ALOS one during the 2007-2011 period and 2016 to 2019 period. Here it shows our comparison, superimpose InSAR measurement to GPS. I just also, probably I should have cautioned you that GPS 3D measurement, InSAR, on the other hand, is a single line side measurement. Whatever measurement project to the satellite loop direction, which range from 20 to 40 degrees from the vertical. So, so this is the at a few different locations. I will show you from time to time in this presentation, show you this stuff. So now I'm going to show you the representative deformation features. So the first feature, of course, we have to show you is the greater Houston area. Here, the substance primarily caused by groundwater withdrawal with some other activities as well. Let's show. I take the Houston as an example of groundwater withdrawal. You can see here we map out the time series for the first time. This time series from the 1990 time interval to 2000 time interval to 2007 to 2011 and to 2000 in the past 2010 to 2020 time interval. So you can see that this Great Houston area, the deformation was very severe in this time window, right? Reached to about 5 centimeters over here. And you can see that the deformation rate decreased pretty significantly. Watch from here, this uplift, this centimeter or 2 uplift is really because the wonderful particles cited by the groundwater districts they put the regulations, and so therefore the substance is curved. And the first was implemented, the substance implemented at Harris and Fort Bend counties, and Mike Turco is really impressive, very outstanding manager on doing this stuff, and the other counties have started following suit. So if you look at what happens in 2007 to 2011 period, you can see that deformation rate is reduced, and also moved to the northwest to these woodlands, cypress, and Katy counties areas. And here we also got limited images over over relatively small area. But here we use the Sentinel-1 data to see what happened in 2016 to 2020. You can see that the rate is reduced. It's about 2 centimeters per year now. And moving out of this area to focus on pretty much for the Katy and cypress, and also the woodland and spring area. So here I didn't show you, but the correlation between groundwater level changes and also the InSAR and the deformation measurement has very good correlation. So we are the groundwater withdrawal is correlated with subsidence and uplift caused by the groundwater rising up, and correlation, the coefficient is about 3.8. And we report this stuff in this paper as well. So because this is not very far from our area, we just want to dive into a little more details here. And here you can see this from just zoom out the pictures I showed you in previous time, show you what happened from 1990 to 2000 to show you the weird amount of deformation. If you are really curious about if you have a house over here, you want to know how much deformation at an individual house, go to our website. You will, if you locate over your house, you will find how much deformation we map out. We present this result on the website. You can go to our website to see whether your house, this particular property is sinking, how much sinking during that time. So when we publish all the other results, we put this results on website for people to digest and use. So you can see again, so substance uplift, localized substance here and there, right? So this is showing what happened in 2012 to 2010 frame. You say what happened later, because we have no SAR images. So that's whatever SAR images we have, we just can use it. So this from 2007 to 2011, and here for the Cosmo data, our limited area, this Cosmo intelligence space agency. And here finally show the data from the Sentinel-1 data that has become available everywhere on the earth. Show the here deformation is reduced, and we call the uplift is reduced, but there's a few hot spots as well. For example, Mount Bellevue and some other locations, we still see quite a significant substance, which I'm going to highlight in a few minutes. So over this area, we also compare with the validating InSAR derived deformation with TPS. Here, the long-term observation. See here, we have the TPS measurements, but we also have ERSAR, ER2, and MSAT and other measurements. See how we are trying to track the deformation measurements compared with TPS. Keep in mind with the uncertainty here, the TPS also plus minus 10 millimeters, right? So there's let's see agreements between the InSAR and the GPS for location. I show you a very interesting feature. You trust, we say GPS benchmark, but I always put a caution because when you these days, when you look at GPS, you really, the first question you ask, what is the GPS measuring? Is measuring surface deformation or deformation beneath the surface, right? Here is a very extreme case that GPS at this ADKS is mounted at the borehole. This is the benchmark. So in other words, this TPS is measure what happened over here. So here is the extensometer measurements. This is the InSAR measurements. We measure the top part in the extensometer over here, and InSAR measurements on the measured surface. You can see InSAR graded with extensometer when they put the TPS at starting at this about 2002-3 time frames. The TPS substance is not that much compared with the InSAR measurements. Well, because TPS is here. But again, even though the TPS didn't show the exact amount of substance on these particular locations, as a function of time. But combining GPS exometer and InSAR allow us to calculate where the primary deformation is taking place. Right? This kind of work will be kind of quantify this kind of process is very important in the future work. So the second substance example is I put in here is a Beaumont Port Arthur, also in Texas. Here, if you know this area, I haven't been to this area yet, but you can see here, this is the we show this Beaumont over this location, zoom out over this area. And this is the from August 1 data 2007, and this is 2014, 16 to 2019 time frame. Okay? So that substance is still going on, but has reduced, and a few locations change from no substance to more substance. But at this area, this square area, this area is actually centered near the Beaumont Municipal Airport. So recovering this the where is there's a lot of gas attraction to groundwater located, and the substance actually during this time can reach to about 3 centimeters per year. So with such substance, I have no doubt people have to do a lot of payment on the airport runway and some other infrastructure issues, right? So groundwater extraction is a primary issue. And so while I'm often tell sometimes groundwater, sometimes gas or oil extraction, because all things are being there different while in one places, and you try to attribute the deformation to a single cause. Sometimes no trivial, right? So we do see consistent deformation from August 2021 during the past decade, but at a reduced rate. So that's the good side, right? So they show the InSAR environment with GPS at a few different locations. Now, the second part of deformation feature I want to show you is substance and infrastructure stability. Here we call infrastructure stability, we like to move to New Orleans. New Orleans area has a long-term substance histories, but believe now the substance for them 2007 to 2010 time frame is not that dramatically much more, put it this way. I'm sorry, compare with the other area, like the Houston Gulf area, which subsiding about 3 to 5 centimeters per year. This is now. But what we see here, taking the data from 2007 to 2011, we zoom out this area, this kind of Mississippi River Gulf Arterial Canal, and over this segment, you see this segment. This is from 2007 to 2011. We see this segment is moving, is sinking something by about how much? By about 5 centimeters per year. Of course, this is also confirmed, actually, can be verified by the airplane measurements. You can do InSAR from airplane as well. So this is published during the UAVSAR data from 2009 to 2011. Interestingly and good that we see this part become very stable after 2015. So something must be done, right? So we also see the deformation of a different period, but show you another interesting feature is over this area. So see this is 2007 to 2011 over this part. This is relatively new development zone during that time. You can see this localized substance which is really associated with the building, with the construction of the buildings. So building put on load, you'll see the deformation. But because it's not elastic processes, right? So it paralyzes that the substance continue and last for years. You can imagine. So it's purely beautiful coupled paralyzation problem. Of course, you can still see hard spot. You can see this building. So if you ask me during this time, maybe this building sinking by 3 to 4 centimeters per year. At this building now, maybe sinking about a couple centimeters per year. And this location, maybe 5 millimeters per year or 10 millimeters per year. You can see hard spot. This comparing with GPS and InSAR environments. What I want to show you this over the New Orleans, city of New Orleans, the substance is not that enormous. Some places you see rising up, depending on the how the water is. So it's from one water point of view is relatively stable, and but the infrastructure stability is an issue. So substance, the third one shows some due to the hydrocarbon. Take the oil, take the gas, you release your pressure release in the subsurface area, and that can lead to the reservoir compactions and the movement of the overburdens of the faults and the localized substance about that reservoir. Show you a few examples over the this is Spindletop oil field and Western Louisiana, Southern Texas, different tracks. So you can see why I'm so crazy to show you data from different tracks. The deformation we see is very small, very localized. So how do we trust the measurements if we don't have ground truth data? So our number one philosophy principle is that we use data from independent measurements. Independent satellite measurements, independent track, because they have different the data acquisition happen at different time, so that will allow us to confirm our observation. Because the noise artifacts in all the uniform is enormous. If you remember my presentation about 3 years ago, if you look at any InSAR images over this area, you don't see any deformation. You only see the artifacts, it's noise. The deformation is really buried by all the noise. Our goal to use multiple temporal InSAR data, try to remove the later deformation from the large amplitude of the noise. That's doable if you have a large amount of data, if you have very good time series spatial temporal analysis technique, including deep learning. So here the RS1 data, I can show you here, and you can see this is the relative stable. You see here the substance over the different locations. These black dots are the wells locations, and showing different time period. You see this is a relative large substance over this location, and the last this disappear because the production changes function time as well. So in summary, we this particularly this southeastern Texas area, you can see this the substance, enormous substance during the 2007 period, and here substance reduced, and based on our latest measurements. So we see more than 20 substance cones related with activity of oil and gas productions. And the substance normally centers at the oil field, conforms to the boundary of the production regime, agrees with the production activity. So if you draw production as function of time and you look at deformation, generally correlated with which I'm going to show you later on for the wastewater injection. The substance rate of course vary temporarily, and some substances persist for decades. So we are 2 centimeter substance, you say, that's who cares? If that substance 2 centimeters lasts for a decade, that's about 20 centimeter of 30 centimeter of substance. That's almost a feet of substance. Will that cause damage to building infrastructure? Should we worry? Should we buy insurance? So this is why we want to do this kind of measurement. Eventually, everybody can use the information for various various way to combat the substance and the source of the hazards. Zoom out to the North Dayton Salt Dome area. The Salt Dome is not only activity is very, very rich, and the deformation we mapped is very eventful. So again, this is a very difficult area to work with. So if you try the InSAR technology, if it doesn't work, don't be despondent. Just look into more detail, look at more time series data, and do fine analysis. You probably will see the T-cell definition. But here we show you the substance and over different parts and change the function from 2 different tracks to provide us some confirmation. And we can see that if you draw profile from A to A prime or B to B prime to here, you can see in here moving down, moving up, and moving down, and this is up, and there's some nodes as well. Are you sure this one? I'm not sure. But this is the uplift. This substance is very, we are very confident. But here, of course, with uncertainty measurements, we didn't draw the error bar. We can put an error bar about there, about 5 millimeters to 1 centimeters. So we don't want to make it very basic, so we remove the error bar. But here, basically, you see what is the uplift the substance. Substance is related to the mining activity, the hydrocarbon house. Uplift is also related with people use this to do the gas storage, and we also doing some fluid injection, some other activity as well. So many of you probably know this area much more than, so I don't want to dive into it. But basically, we can dive into to look at a very eventful deformation in fine scale. So the substantive hydrocarbon show you another Corpus Christi. I visited this area 4 years ago. It's very wonderful places. But this is a well-known substance with this one. So we know this substance particularly from 1940 to 1970, more than 1.5 meter substance was reported. So we obviously we look at 2007 to 2011, 2015, 2019, the substance, there are still substance over areas, but substance in some places reduced, and not really for this case, you can see for here, probably a little bit moving intensified over a few, over this area. So another hydrocarbon related activity over this part is Mount Bellevue. I mentioned to you a few slides ago, show the substance over the 2007 to 2011 period and show reduced substance in the past decade. So the comparing with the substance at about our environment with GPS. So the fourth type of feature we classify called salt mining. Salt mining, let's move into the Louisiana, this area. We look at this area. This is this area called the Five Islands. So this particularly you can see these features, the Five Islands for the Stephenson, Avery, and the Weeks, and some other islands. Right? So I haven't been to this area. I don't know much about geology here, but this is salt mining, and we can see here is we zoom out a few locations. For example, for the Avery Island, for this area. We can look at the deformation over this area. So we can see the western part is sinking, and particularly over this weak island, we can see right part sinking, eastern part is sinking, but at a reduced rate. So what is we see the maximum substance reached about 3 to 4 centimeters per year, and that happened at the center of the mine. It is also aligned very nicely to the location of the salt mining works. So for example, at the Weeks, the western substance is much more than the eastern part of the substance because the mining mechanism used for the west part, I think they used conventional room pattern mining technology, which involved heavy machining. And the eastern part, I think they use solution mining. So over this island, you can see that beautiful substance feature over here, right? More than 60 centimeters is more homogeneous. You can see this the deformation environment has high signal ratio, and they are confident. So the fifth type feature is called surface uplift. We talk about 2 months substance. Let's talk about the not good part of the uplift. That is, so this is really associated with this the wastewater injections and also the wastewater disposals. The injections is really for the enhancing oil field, and disposal is a really byproduct of oil gas production. So the deformation associated with the feature normally very localized, very rapidly developing, tend to correlate very nicely with the production, with the deposition. So we identified this deformation range to a few centimeters up to 6 centimeters per year, and many cones, and many cones are less than about 2 kilometers. Of course, depends on the types of the injection, right? So some of them actually keep rising for more than a decade. So if the ground is sinking for 5 centimeters per year for 10 years, you have half in some here, you rise about 5 meters. That's so equally hazardous as well. So of course, I'm going to show you a couple of examples here. You can see this beautiful show the uplift for different time period of this location. You can see the well number here, and particularly let's look at this one, and you can see this different time period from 2007 to 2010, 11. I'm sorry, the timing. 2015 to 2019 here. You can see this is the volume. It's a volume here, and you see the uplift. Over this area, we don't see deformation, and then we can still see a little bit of uplift here and see substance because of the stop the injection. So obviously, it's beautifully characterized by the polarized processes. So we haven't done much more into. We have past 3 years we focus on mapping and imaging future work will move into more on the modeling and calculating the deformation phenomena. Right? So there's many things you can propose. So here, my PhD student Wei Yu, I think she's almost like a detective. She like to see, take an example with publication of the wastewater injection here slightly out of the Gulf Coast in the West Coast, in West Texas, near the permanent near the Pecos area. So they show very localized area. Over this area, you see this about a 5 centimeter per year deformation uplift lasts for 3 to 4 years, totally 15 centimeter of deformation. And they show you the different aquifer system over here. I don't want to dive into here about detail, but you see here, this is the show time series InSAR measurements, right? And this show you the production, the wastewater injection volume. So the deformation centered at almost near at the injection well correlated with viral. So it's reasonable to deduce, say, the inflation, the uplift was caused by the wastewater injection. So now we see this stuff, but when you look at the deformation detail, she's puzzled. That is the observed deformation here. That is the spatial extent cannot be explained by the amount of volume by the depth. So the reported depth 1 kilometers, but you can apply elastic model. You can apply the with fully covered polarized model. Yeah, the best fit model for both elastic model and for as well the polarized model indicate us this is less than 150 meters. Why the injection about 1 kilometers and all the merit deformation is 130 meters. So this make us suspect most of them probably experiencing leakage due to the casing failures and the sealing problem as well. We recently published a paper, not recently, really this is a published paper, how our area become purely a land or abandoned well, that then the substance happened on that area and the pounding of the water, and then that area become a waste or become a lake and disrupt the county road as well. So this is something we are trying to dive into more. And the final feature I want to mention to you is faulting. So the people have done, from Professor Khan at the University of Houston, done wonderful work on mapping the area with LiDAR data and by several projects. So the white out of LiDAR, this is our InSAR environment. So keep in mind, there are two different things. LiDAR using the topography and the relief. The InSAR has nothing to do with topography. We are measuring how the active faulting, right? Whether this the feature revealed by LiDAR happen to be feature revealed by that can happen in recent years or maybe long ago, depending on the time. But the InSAR only measure what happens, active movement along fault. Here we look at the dashed out show our measurements, and this show the LiDAR measurement. We see agreement between two, and on the other hand, we infer additional information from InSAR measurements. Zoom into field detail. This will allow you to appreciate, and this is every day I'm enjoying this moment when students present me doing that. You see this one on this part of fault, right? We see this kind of amount of average deformation on this part of fault. How much the difference is less than 10 millimeters per year. That's what we can see. Here, look at another fault. We can map out the deformation amount on this part of fault, and on this part of fault. So here, so all the measurement confirm can be, agree with the ground-based LiDAR measurement, seismic reflection, and some other electromagnetic measurements as well. So most measurement, I think we see the fault is striking parallel to the Gulf Coast dating, normal faulting dating to the southeast. So that concludes my talk. So we say, well, we constructed for the first time deformation map over the half million square kilometer of the Gulf Coast area using these two major data sets of data. We identify many subsidence tones and many active tones. And a lot of deformation, transit meter can be reviewed by the sending run data. And of course, the deformation over the Gulf Coast, I hope you take the message, is can be caused by many causes. And here I'm now primarily focus on human-induced anthropogenic factors, including groundwater hydrocarbon extraction and injections, faultings, and salt activities. there are some natural compaction on that part because so small we haven't addressed that part yet. So provided was a similar picture deformation, and this is will be very useful to comparing with GPS and InSAR to do hydraulic model. So I think I'm going to stop here, and I think because I ran out of time, I don't want to show you a video, but basically here is my message to you. That is, we spend much time to do that deformation, but this work can be much easier done because the game changer is coming. What is game changer? That is, US and India is going to launch a satellite called NISA combination, 2 band sensors, first time on a single satellite provide priority repeat 10-meter resolution anywhere on the Earth. With this kind of data, we can provide a golf course deformation much easier with high accuracy. So this can obviously is a game changer to start a solid processes. So I think I will stop here. Thank you for listening.
All right, great. Thank you, Zhong. Let's open up for questions from audience. Is there any question?
Well, I have a question while people and graduate students are thinking of questions. Very interesting talk, Zhong, thank you.
Thank you.
You show beautiful examples of ground deformation. And of course, those are a boundary condition to what the 3-dimensional deformation